Hello everyone, I'm Jason, and today I will talk about how to display hundreds of videos simultaneously on iOS. Before we start, a bit about myself. So I've been working at AMO for the last 2 years, and at AMO I wear many hats, I do a lot of things. First thing is I'm an AI agent manager. I manage AI agents because they are easier to manage than you. Also, I'm a full-time chess master. I won the first place at AMO Chess Tournament. I'm discovering some of the slides with you. And except that, more seriously, I'm owner of core features of the Bump app and the map experience. Let's start with the challenge. So what we're trying to do here is to display all those cutouts. So cutouts are the profile picture in all the AMO apps. Those cutouts are basically a record of the user face with the background removed, like a small record of 2 seconds. They are great. They give a liveness to the map, and we love them. The issue is that it can be very hard to display all of them. So this is the original data. You can see that it's a WAR video in 2 parts. In the top part, you have the actual record, and in the bottom part, you have a mask. This mask helps us to achieve transparency. We could have record it in HEVC with transparency, but unfortunately, it's not compatible with Android. So we needed a way to achieve that. So that's our way. So we have like a custom pipeline process that takes this video and outputs the actual frames that will display on screen. So our solution to be able to do that is a UIImage array-based solution. It can be surprising, but bear with me. So the first step is that we download the original video and we store it on disk. Then we process that video through our pipeline to extract the frames and apply all the transforms needed. And then we display the frames one by one over time with a UIImage view. Looks like this. So here we can see each frame that will be displayed on screen, and they are extracted as individual images. This solution is nice because it's pre-decoded and pre-transformed frames. Here you can see that we added a border to each frame, and it optimized the playback time for us. Then we just display them one by one, and that's it. This approach doesn't need to decode any frame on the fly. You could use an AV player to play a video, sounds logic, but the issue is that it's based on hardware decoders that are limited, and once you are starting to have 20 or more, you just can't anymore. The approach with UIImage, and I will talk about this trick, allows us to display those videos with a 0% CPU usage during playback. That's because the UIImage view animation images is an awesome API. This API allows you to provide an array of images and a total duration. Then you call start animating, and it just plays those animations. And surprisingly, it does so without using the CPU. I mean, without using the main thread. And like a lot of UIKit APIs, it's just a wrapper on top of core animation. And core animation does all the magic. The magic here is that we are leveraging the core animation render server. Basically, core animation, when you create an animation, you create a transaction, you pass it to the render server, and you offload the work on that server. The render server is out of your process. That's why it's reporting 0% CPU usage. because it's not done by the main thread, it's not done by your process, it's done by the GPU. So the main thread is happy. Now let's think about the state of the device. So with this solution, the CPU is chilling, not much to do. He's only used during the process time, so once per cutout. The GPU is just swapping some UI images, very reasonable. The disk just store the cutout, that's okay. But the RAM is suffering a lot. Because basically, what we are doing is we are keeping the array of images, and it's 60 images because it's a 30 FPS video over 2 seconds. We are keeping the bitmaps in RAM. That can eat up like to 20 megabytes per video. The playback is great, but the memory is suffering. So the consequences of this are a bit hard. We have built a cache in memory that allows us to limit the total space used by the cutout. We want to limit it to 200 megabytes, for example. But what happens when we hit that limit is that we have to drop some of the old cutouts from the memory. Meaning that if you want to redisplay that cutout, we'll have to redo the processing and redo the CPU intensive part. So we need a way to reduce memory usage somehow, but keep the very good performance at playback. And that's when we had a lot of difficulties to find something. We stayed in prod with this solution for a few months. Users were happy. I was not. Then, so I was rambling about that once again. And there is this guy, Alex. He's like a Rust engineer. He's like always like, what about we rewrite everything in Rust? So he was like, you should try ASTC. And I was like, shut up, Alex. Is that a new way to say that we should try Rust? Turns out it was not. ASTC, it's very not known API. It's a texture compression format. The benefit of this format, you can think about it like PNG. It's a way to compress images. The benefit of this is that it's GPU native. That means that you can pass an ASTC texture to the GPU, and the GPU will be able to display it directly. So that sounds promising. So adaptive, scalable texture compression. Adaptive and scalable means that you can choose your compression level, basically. It's a lossy process, but you can choose how much compression you want to achieve. So take a bitmap. A bitmap is a very good format, a very simple format. You have 32 bits per pixel. It maps for each pixel the color. With an ASTC, you can go down to 1 bit per pixel. Quality may suffer for that, but that works. So let's check the support of this strange techno. It's supported by Apple GPUs since A8. It's iPhone 6, basically. LDR here means that it's low dynamic range, so it's HDR since the iPhone 6. It's also supported on most of the platforms, more or better, but it works. So let's see how to use ASTC on iOS. So on iOS, normally when you want to use ASTC, you use it with metal. You load a metal texture, and you can give that texture to the GPU and display it, apply it with a shader. I won't go into the details, but classic metal stuff. It's not fun. So we could have used that. Sounds promising. Sounds interesting for the RAM, but in the same time, the issue is that we cannot use our playback strategy. that allows us to free the main thread completely. So we needed a way to leverage ASTC, but with our array of UIImage. So let's think about UIImage. What is UIImage? UIImage, under the hood, like a lot of UIKit stuff, is just a wrapper. It's a wrapper on top CG image. So the CG image has an interesting feature, which is that when you load a PNG from disk, for example, it has the ability to not actually load the whole data, the whole bitmap in the RAM. It will wait for when you need to display it to load it from the map. That means that it has some asynchronous behavior that we could maybe leverage with our STC data. So that's what we try to do. So the idea, to recap, is with STC, we could decompress that data on the fly, pass it to the GPU, and for each frame, the GPU will just get the ASTC data. So in RAM, we keep the ASTC compressed data and never get the bitmap stored in our RAM. And if you manage to generate a UIImage with an ASTC-baked data, we can still play it back with UIImage. So now, how do we manage to kind of smuggle this ASTC into a UIImage? So the idea is to encode each frame to ASTC, and then load the frame using Image.io. It's like a sub-framework of core graphics. And then with that, generate a CG image that will be the backing image of our UIImage that will be displayed by the UIImage. I won't go into the details, but that's basically what we managed to do. So the end result is that the UIImage is now showing an ASTC compressed frames. And that's worked. But using ASTC UIImage that way is totally undocumented. Like if you look in developer.apple.com, you won't find anything. The only references to ASTC is about metal textures and not how you could use that with a UIImage. But we found in Apple texture encoder.h, by looking for ASTC stuff, that there are like a documentation that says, save yourself some time, please read this. And this is the header of a masterpiece of engineering. This basically do all the work. You need to call it with some low-level APIs. But if you are looking to use this kind of techno, take a look at this header and read this block. And there's another block of text, and enjoy. So a few takeaways. Gaming industry, they know how to draw pixels. They know how to store textures. And if you need to deal with this kind of thing, take a look at what they are doing. They have like a lead on us for that. About the resources, it's always a game of balance. We often have the CPU that is overused because the main thread is the bread and butter of the UI. But if you can do UI stuff outside of the main thread directly by the GPU, you free your main thread, and then you can do a lot of other crazy stuff with the main thread, which is often needed. So here, the gains were basically to use more the GPU and less the RAM and the CPU. If for some reason you are keeping plenty of UIImages that are not backed by a resource in RAM, consider using ASTC. So the next steps for our animated contents. So I talk about animated content because I'm talking about the profile pictures, but there is not only that in the Bump app and the other apps. We have a lot of animated content. Some of them use the same strategy. So next step for us is to try to store the ASTC directly on disk. If you store the ASTC on disk, we can avoid doing the pipeline. We do the pipeline once, and then we cache this on disk. We could not have done that before ASTC because it bitmaps, and sorting 60 bitmaps is very heavy. So with ASTC, divide this size by 5. So it starts to be something we could consider. The issue is that we have some variation of this pipeline, some with some in black and white, some with corner radius, pre-applied, some with border, and all of that is that means that for one single frame we'll have 5 or 6 variations. But it could help us if we manage to do that to remove the RAM cache altogether. Basically, it's kind of an ambitious idea, but the idea would be that using the closure-based API on UIImage, we could potentially memory map the file from the disk, read it on the fly when the CocoaHeads need to display it, load it directly in the GPU, and never keep even the ASTC representation in the RAM. But we still need to test that, and that's it for me. I want to thank Clément Kess, who is like a math expert, low-level stuff, implemented this stuff in 2 days. When we explained to him that we wanted to try ASTC. Thanks to Alex for the idea of ASTC and the whole iOS team. By the way, here you can see our iOS team. You can see our cutouts. And those are the crazy guys helping to do all of the stuff. Do you have any questions?
Great job. Taking from game development, always good. Have you tried the sprite approach? Load the whole texture once and scroll through it?
I think we tried that. I don't remember exactly what was the trade-offs, but basically what you mean is generate an atlas with so instead of generating an array of image, we generate just one atlas and we swap the
position in the window.
The position, yeah. It doesn't gain much because
with ASTC.
With ASTC, yeah. That's our plan. If we plan to store the ASTC on disk, it will be on an atlas.
Yeah.
But that's the next step. If you store it on disk, it will be it has to be in an atlas. But for the current one, where the ASTC is only generated from the video and stays in RAM, we don't really need it.
All right, thanks.
Thanks for the presentation. You said that if you are storing plenty of UIImage in RAM, you need to consider ASTC. For from how many image did you start to find that you need to use ASTC, suffer from performance or something like this?
Basically, we had like a cache of like a hard limit around 200 megabytes. We didn't want the cutout to use more than 200 megabytes because we have plenty of other features that need to use the RAM, that need to use the CPU, etc. So those 200 megabytes were hit by our video with just 10 or 15 cutouts. So starting at 15, we are starting to see cache eviction because the cache was hit, so we need to drop some of them. So it will depend what are your limits, and we didn't want like 1 gigabyte of the RAM to be used just for the cutout. But even with 1 gigabyte, it means that you could store maybe I don't want to do the math, but a few hundred of those stuff, and not a few, like maybe 50, but yeah, it will start to be a limit because like you have a cutout for friends, but also you can see the profile of a friend and their friends, and yeah.
Okay, thank you.
But each cutout is like 60 frames. So when I say 50 cutouts, I mean 3000.
Are you reducing the pixel resolution of the original video before transferring it to ASTC?
So there is the processing part that I didn't talk a lot about it, but it's quite interesting. So what we are doing there is first we are doing the mask. We are masking to get back the transparency. Then we are doing a resize to scale down to the size we need to use it. Then we are doing border, apply border, then the style, basically black and white, add the gradient, you also add the gradient border to smooth the alpha not go from to 0, etc. So yeah, it's part of this processing.
Thank you.
I was just wondering, is there any specific compression artifact? You mentioned it was lossy that we can find on this ASTC.
I remember when I implemented it, we had to fight with pre-multiplied alpha stuff because the simulator behaves differently than the device and that. But the compression, basically we choose a compression that was not noticeable for us, for our use case. So it's a magic number of 0.7. It gives us like 1 to 5. I mean that for something that, yeah, like divide by 5 the size. And at that size, we didn't have artifacts. We had some artifacts, but it was because of multiplied alpha bugs. But except that, it's fine.
Okay.